In this lesson, we're going to introduce the laws of thermodynamics. The basic goal is just to give you a statement of all three of these laws with some applications. First up is the first law of thermodynamics, which tells us that energy is neither created nor destroyed. That means the amount of total energy around stays constant. We don't get rid of it, and we don't gain any. And we can express that with a mathematical equation, which tells us that delta E, which is the change in energy of some object, is equal to any heating we do, that's what Q stands for, strangely Q stands for heat, and any work we do on the system, which is W for work. That one makes more sense, right? And we have an example of transferring energy of heat in this pot of water. We've turned on the stove, and we've applied heat to the water, and it's made the water hot. What the conservation of energy would tell us in this case is that we couldn't get the water any hotter than the amount of heat we applied. We don't suddenly get new energy from somewhere. And if we've applied a certain amount of heat, it has to go somewhere. It can't just suddenly be destroyed and have the water get colder, for example. That would be nonsense. So the amount of energy has to be conserved. We can transfer energy as heat, or we can transfer energy as work. And that's what we have over on the right, someone pushing a car. And the conservation of energy would tell us that if I push a car and give it, say, 10 joules of energy, then that's the most the car's energy could increase by. We don't suddenly get energy from some other place. An interesting application of the first law is a Newton's cradle. So here we have Newton's cradle, and you may have seen one of these, but we take one of these spheres and we pull it back. So that's doing work, turns out. And then we release it and it goes forward, and the energy is transferred through these metal spheres until it gets to the end sphere, which then kicks up and then drops back down. Now, over time, what happens is these spheres run into air molecules that are all around, which creates friction, which means that some of the energy goes away in terms of heat as those spheres travel through it. And eventually, the spheres will stop moving. Now, if you put them in a frictionless environment, they'll just keep going. But what do we know about the amount of work we put in at the beginning and the amount of heat that comes out at the end? Well, they have to be equal. So all of the energy you give to that sphere in terms of work by pulling it up goes right back to the surroundings in the form of heat, and those two magnitudes are exactly equal, and we know that because of the law of conservation of energy. Okay, the second law is about entropy. It tells us that the entropy of the universe constantly increases. Cool, but maybe we want to know what entropy is. Well, there's two main ways to talk about what entropy is. First up, we'll talk about it as disorder. So we can think about entropy as a measure of disorder. In this case, what this law is saying is that the disorder in the universe constantly increases. Things tend to get mixed up and messed up. Glass shatters and sand spreads. So things spread out and get mixed up. That's what that law is saying when we think about entropy as a measure of disorder. We can also think about entropy as a measure of energy not available to do work. And in this case, what this law is telling us is that the amount of energy around that we can use constantly decreases. It's never going to get more than it is right now, and it was more a million years ago than it is today. The amount of usable energy is constantly decreasing. An example, when we think about the entropy in terms of disorder, is dissolution, something dissolving. Here we see a beaker that we've put table salt into, which is sodium chloride, and we have that represented in yellow and green spheres over here. So this is a nice chunk of sodium chloride. And when I have a chunk of sodium chloride like that, you can see it's in a nice, regular, ordered structure. But what happens over time is it dissolves and spreads out into the water, and we see that the negatively charged ions and the positively charged ions go disperse and mix up throughout this whole solution. And that's an increase in entropy. And so this process is favorable. Dissolving things, really straightforward. It happens automatically in most cases, and that increases the entropy. On the other hand, doing the opposite process would be a decrease in entropy. Turns out that a decrease in entropy can happen as long as there's something offsetting it elsewhere. That gets into more details we won't really cover. But the point is that overall, altogether, the entropy of the universe constantly increases. If we think about the first and second law, we can do something kind of interesting. We can track the energy in the universe over time. So we're going to draw ourselves a nice little graph. And on the x-axis, we're going to put energy. So we're thinking about energy here. And on the y-axis, we're going to put time. All right. Here, we're going to put time 0. So this is the beginning of the universe at the very far left. All right. At the beginning of the universe, let's say we have this much energy. The question is, let's say all the way out at now, which is, a long time from the beginning, how much energy do we have? Well, as a consequence of the first law, we know that this amount of energy present in the universe just stays totally constant. It doesn't change. So total energy just stays the same. we always have the same amount of energy, the amount of energy we had at the beginning of the universe. On the flip side, how useful is that energy? Well, the first law tells us that our total energy stays the same. The second law tells us that if we think about how much usable energy we have, at the beginning, maybe almost all of it was usable, right? So at the Big Bang, the entropy was really low. Now, over time, the entropy increases, which means usable energy drops and drops and drops. So what entropy increasing does is it drops the amount of usable energy. So this orange line is telling us about usable energy. And the usable energy constantly decreases as we go forward in time. Eventually, there will be no more usable energy. The suns will go out, the stars will not burn anymore, and the energy around will all be dilute, useless, high entropy energy. So by using the first and second law here, we can think about what's going to happen to the total energy in the universe and the usable energy. Okay, the last law of thermodynamics we're going to look at is the third law, and it is the last law. It tells us that the entropy of a perfect crystal at 0 degrees Kelvin is 0. So here, once again, we have a perfect crystal. So this could be an ionic compound, and it's stacked together in a super orderly way. And what the third law does for us is it gives us a 0 point, a definition of what is absolute zero entropy. And the entropy of a perfect crystal at 0 Kelvin, so that's at the coldest possible temperature there is, where all motion stops, is 0. So this just provides us with a 0 point for our entropy. Here I've summarized the laws of thermodynamics. You'll notice I've changed the wording just a little bit, and that's to get you to feel a little flexible with how exactly these are stated. You'll see them stated differently all over the place. Different textbooks will have slightly different statements, and on the internet you'll find slightly different statements. So the first law here is stated as the energy of the universe is conserved. That's the first law of thermodynamics. Mathematically, change in energy equals Q plus W. The second law looks pretty different here. It says spontaneous processes always increase the entropy of the universe. And that's basically just saying processes that happen, that's a spontaneous process, is going to be one that increases the entropy of the universe, which is consistent with the way we stated the second law before, which said that the entropy of the universe always increases. And lastly, the third one, you don't see much variation in how it's stated. The entropy of a perfect crystal at absolute 0 is 0.